Hello everyone, welcome to problem 4.20 of David Griffiths Electrodynamics. So real quick, this is going to be a fairly short problem compared to the last one, but essentially what we have is we have a sphere that's made up of a linear dielectric material, and embedded in it is a uniform free charge density of rho. So there is a volume charge, there's a free volume charge that somehow is, got into this linear dielectric material. That's all we really know. And we want to find the potential at the center of the sphere relative to infinity if it has a radius of r, capital R, and the dielectric constant is epsilon sub r. So to do this, of course, the potential we know is going to be the negative line integral of E dot dl. So we're going to need to know the electric field. But since we know the free charge is rho, we can use, it's going to be easier to use Gauss's law for the displacement field and find D first and then find E. So for inside of the sphere, and we're going to need to know the electric field inside the sphere and outside the sphere because we have to integrate from infinity to the center. So the electric field as we're going from infinity to the surface is going to be the electric field outside. Oops. And then when we're integrating from the surface to the origin, that's going to be the electric field inside. So we need to know both. So we know Gauss's law, of course, for D is the flux of D is equal to the free charge enclosed. And if we make our, and for this case, we're going to do inside. So if you make our Gaussian sphere some sphere that's smaller than radius r, then the free charge enclosed, D is going to be constant. The surface area of our Gaussian surface is 4 pi r squared. And then the free charge enclosed in our Gaussian surface is just going to be rho times the volume of our Gaussian surface, which is 4/3 pi r cubed. Then solving for D, we get that D is 1/3 rho r. And then E is related to D by this relation, D over epsilon. That's from 4.35 in the book. So then we just divide D by epsilon and we get rho r over 3 epsilon for r less than the radius of the sphere. And then for r greater than the radius of the sphere, our displacement field ends up being, our surface area, the left-hand side of Gauss's law stays the same, but the right side ends up being rho times 4/3 pi capital R cubed, because our Gaussian surface encompasses the entire sphere here. So it'd be the total volume of the total charge enclosed. So then when you solve this for D, you get rho capital R cubed over 3r squared. Then when you divide D by epsilon, you get rho r capital R cubed over 3 epsilon r squared for r greater than r, for r greater than capital R. So those are our two electric field, this one and this one. These are our two electric field values for inside and outside the sphere. So then when we do the potential when we find the potential minus E dot EL from infinity to 0, we're going to first break this integral into the integral from infinity to the surface with a minus sign out front using the electric field for outside the sphere. And of course, the DL in this case is just going to be dr. We know the electric field is going to be radial, so just by symmetry, so the dot product just gives us the dr there. And then we have minus the integral from r to the origin, the surface r to the origin, and then we use the electric field inside the sphere for that second integral. So this first integral will give us a minus 1 over r, so that will cancel the minus sign out front, and we get rho or capital R cubed over 3 epsilon naught times 1 over r, evaluated from infinity to capital R, minus, and then this integral will be r squared over 2, so we get minus rho over 3 epsilon r squared over 2, evaluated from capital R to 0. So this first integral, when we evaluate it, is going to just give us, it's going to give us a capital R on the bottom, which will cancel an R on the top, but then the second bound, when we plug in infinity, 1 over infinity is going to give us 0. So the second bound just becomes 0. So we only get one term from the first integral. Sorry, let me just erase that. And then for the second integral, the first bound will give us 0 because we're plugging in 0 for r, but then you have a minus from the subtracting the two bounds, and the second bound you plug in r, so you get r squared. So this minus sign and the minus sign from the minus sign because of the relation to the potential, those will end up canceling and get a positive there. So you end up getting a similar relations here. So you get this one has a factor of 6 on the bottom. This one has a factor of 3, so I get a common denominator, so I multiply this by 2 over 2. So I get 2 rho r squared over 6 epsilon naught plus rho r squared over 6 epsilon. Factoring out the common stuff, so we get 3 rho. So 2 over 6 plus 1 over 6 is 3 over 6. So 3 rho r squared over 6. And then with that factored out, we have 1 over epsilon naught plus 1 over epsilon. And then 3 over 6 is just 1/2, so that's rho r squared over 2 times 1 over epsilon plus 1 over epsilon r, because epsilon is just epsilon naught times epsilon r. And then factoring out a factor of 1 over epsilon, we just get rho r squared over 2 epsilon naught multiplied by 1 plus 1 over the dielectric constant epsilon r. And that's just going to be my final relation then for the potential difference, the potential at the center of the sphere. All right, that covers problem 4.20. I hope that helps you guys out. As always, if this videos or my other videos help you out, feel free to leave a like on the video, subscribe to my channel, take a look at my membership options. I offer early access as well as typed LaTeX solutions to these problems as well. So take a look at those if you're interested in that. Otherwise, I will see you all on the next video.